I did my chemistry presentation over titration curves. Today, I will talk about what titrations and titration curves are, the history of them, and information regarding the different types of curves and how they are used in the classrooms and labs. First, what are titration curves? A titration curve is the plot of the pH of the solution versus volume of titrant added as the titration continues. Before a titration curve can be drawn, a titration has to take place. Titrations take a solution of known concentration, known as the titrant, and use it to determine the concentration of an unknown solution, known as the analyte. A titration is complete once the amount of titrant has completely neutralized the analyte solution. This is called the equivalence point. There are 4 specific types of titration curves that I will talk about later in the presentation. Those include a strong acid, strong base titration, weak acid, strong base titration, a strong acid with a weak base, and polyprotic acid titrations. Before I continue on about titration curves, I want to briefly mention some history. They originated in the late 18th century by French chemists. It all started after the first burette was further developed to be utilized in a titration. To the right, there is an image of what a burette looks like. It may look familiar as we have used them in lab before. Once titrations were developed, drawing the process into a curve soon followed. To have an idea of when a titration has ended, indicators are used. Indicators cause a color change in the solution and signals the endpoint has been reached. The best indicators to use are those with pHs similar to the pH change of the reaction. For each type of titration curve, there is a specific indicator that is best to use. In our chemistry labs, we used phenolphthalein as a weak acid indicator. If you remember from our labs, our solution turned from a clear solution to a light pink solution. As already illustrated, we use titrations to determine the concentration of unknown solution. The pH of a solution at equivalence point is dependent on the strength of the acid and base. The picture to the bottom left illustrates what the titrations look like. Hypothetically, if we were actually in the lab, the purple solution that is in the conical flask would turn to a different color because of the indicator. Indicators make it easy to utilize titrations in lab to create a titration curve. Besides lab, there is also a lot of information a titration problem can give us in the classroom. When sketching a titration curve, it is important to remember to decide whether your acid or base is strong or weak, and to label your axes. The problem on the right is an example problem that we have calculated many times before. You need these scenarios to calculate the volume that has been added to reach the equivalence point and estimate your pHs. Based off the questions, it is easy to find the starting pH, buffer regions, pKa or pKb, and equivalence point. The K value on a titration graph is either the Ka or the Kb. The Ka is the acid dissociation constant, and the Kb is the base dissociation constant. To obtain pKa or pKb from Ka or Kb, you just have to take the negative log of it. pKa is the same as the half equivalence point. So in other words, pKa equals pH. So that would mean pKb equals pOH. Therefore, to find the pH of a base, you would just have to simply convert the pOH to pH by subtracting it by 14. Once all the information is calculated, it can be plotted on a curve. There were 4 types of titration curves that were mentioned before. The first one I will discuss is a strong base, strong acid titration curve. An example of this type of curve would be hydrochloric acid and sodium hydroxide. The graph can either have the volume of the base or volume of the acid on the y-axis. but for sake of time, I will only talk about the graph to the far left. Let's say we start attempting to draw this titration curve. We would plot the NaOH on the x-axis and pH on the y-axis. We wouldn't add any NaOH for point 1, so the pH is pretty low to start. As NaOH is added, the solution will become more basic until it hits the equivalence point and levels off. For strong acid, strong base titrations, the pH at the equivalence point is 7. Additionally, the best indicators to use are methyl orange, methyl red, and phenolphthalein. The next type of titration curve is a strong base with a weak acid. Every weak acid has a strong conjugate base. An example of this would be acetic acid and sodium hydroxide. Acetic acid is the weak acid, and sodium hydroxide is the strong base. When you react them together, water is the conjugate acid of OH-, and sodium acetate is the conjugate base of the acetic acid. As illustrated in the picture, the initial pH is acidic. But acetic acid is a weak acid, so the starting pH is higher than what a strong acid would be. At the equivalence point, the pH is above 7. The best indicator to use for these titrations are phenolphthalein. The third type of titration curve I'm going to discuss is a weak base, strong acid curve. Similarly, every weak base has a strong conjugate acid. This curve is almost flipped from a strong base, weak acid titration curve. An example of this titration would be hydrochloric acid and ammonia. So the hydrochloric acid is the strong acid and the ammonia is the weak base. The conjugate base pair of HCl would be Cl-, and the conjugate acid pair of the NH3 would be NH4+. As shown from the curve, it starts off as basic, but when you add that acid, it shoots down and levels off to become more acidic. The equivalence point is below 7, and the best indicators to use are methyl red or orange. This is a weak acid, strong base polyprotic acid titration curve. If you've noticed, it does look different from the previous monoprotic acid curves. That is because there are multiple equivalence points. Polyprotic acids display as many equivalence points as the number of acidic proteins they have. For instance, a diprotic acid would have 2 equivalence points, while a triprotic acid would have 3 equivalence points. This picture shows a diprotic acid curve, illustrating the steep pH climbs and its steadiness at the midpoints. An example of this curve would be carbonic acid, because it contains 2 hydrogen atoms per molecules capable of dissociating. However, each proton isn't released at the same time, but rather one at a time. Consequently, the first Ka is always the largest, followed by the second. To illustrate this dissociating, the picture looks kind of like steps compared to the S-shaped curves from the previous titrations. The carbonic acid has a conjugate base pair, NaHCO3, and the sodium hydroxide has a conjugate acid pair of H2O. In summary, in an acid-base titration, a known volume of acid or base is placed in a flask, and the second reagent is placed in the burette, where it is slowly added to the reagent in the flask. Acid-base indicators are compounds that change color at a particular pH. This helps indicate the equivalence point. A titration curve is the plot showing the change in pH versus volume of titrant added. Throughout the presentation, I have discussed 4 specific types of curves. I illustrated the important points for each curve, especially highlighting if the equivalence point is above, below, or equal to a pH of 7. Here is a list of my references. Thank you for listening.